So, we got egg, we got sperm, we got gametes. And those gametes have, for humans, one copy of all 30,000 genes that a human being is composed of. And, some of those genes there really aren't two distinct varieties of. The gene that tells your cell how to build a cell wall, you all get a cell wall, you all get the same version. There's no different size or shape or color. For the traits that we've been talking about that are Mendelian traits, where there are two alleles, and it might be, wrinkly or smooth seed coat. It might be, normal mucus or extra thick mucus like in a CF patient. For the things that are Mendelian traits, we can look at all the alleles that exist in that egg. So we've up to now been doing things like big E, if a mother is... So I'm using the big N, little n sort of generically. This could be for any trait. If mom is big N, for every egg she produces, we have said that there is a chance that that egg will get a what? Big N. There's a chance that egg will get a little n. For every sperm that a male produces, if he is heterozygous, he's big N, little n, there's a chance that that sperm will get a big N. There's a chance that that sperm will get a little n. It's really easy with one trait, but we just said traits are not passed on one at a time. So what we're going to start to look at is a dihybrid cross. Guess how many traits we're crossing at one time? Two. Di means two. We could do a trihybrid cross. We could do a quadrahybrid cross. We could just keep going, and I'll tell you a funny story about that later. So let's say, I'm going to get rid of these. Let's say that we're looking at two traits for mom and dad. We don't know what the traits are. Maybe this is nose color and tooth size. We're back to our beavers, but that's okay. So if mom is heterozygous for both traits, every time that she produces an egg, there is a chance that that egg will get a big N, or there is a chance that that egg will get a little n. Right? Yeah, we just said that, Moser. We know. So every time she produces an egg, every egg that gets a big N could either get a big D or it could get a little d. Is that true? Yeah. If these traits are assorted independently. As long as these traits are not linked together in any way, as long as these genes are not connected in some way, and it's really truly just random assortment, every egg that gets a big N could either get a big D or a little d. Well, every egg that gets a little n then could either get a big D or a little d. So how many combinations do we have possible for her eggs? There's a clue right up here. That would be in the number of boxes, the number of eggs that I've just drawn. So we could have a big N, big D bearing egg. We could have a big N, little d bearing egg. We could have a little n, big D egg. And of course, our last combination, we could have a little n, little d egg. So with just two traits, if the parent is heterozygous for both of them, there are now 4 possible combinations for their gamete. How many traits did we say there were in a human? How many genes? Like 30,000? Oh boy. So, if we look then at dad's gamete production, we look at those sperm, how many combinations do we get? Okay. So for each of these parents, we have 4 possible combinations for gametes. What we're going to do now is put those together into a dihybrid cross. Have you done dihybrid crosses before? Okay, so what I'm going to have to do is put one of each of the possible gamete combinations across the top in each sort of column. So I'm going to put, these are my eggs, big N, big D, big N, whoops, big N, little d, little n, big D, little n, little d. I'll sort of cheat that one. So that's the mother's potential contributions. Down the side for the father, I'm going to do the same thing. I'm going to list all the possible all the possible allele combinations we would expect to find in his gametes. Big N, big D, big N, little d, little n, big D, little n, little d. Okay. So now what I'm going to do is I'm going to cross these, but I'm going to keep the alleles for a particular trait together because we're showing the genotypes that are possible in the offspring. So this one would be big N, big D, big D. It is homozygous dominant for both traits. And you're going to continue to fill them in just like that. Whew, that's a lot of possible combinations. So important things to note. You have to keep the alleles for a given trait together, you know that. The capital letter goes in front when there are two alleles for the same trait. People often get confused by things like this because there's a lowercase letter in front. That's because we just try to stay consistent with keeping a particular trait in the front all the time. That's not expressing an organism's genotype. That's expressing the combination of alleles that are present in the gamete. So it's different. So after we do a Punnett square, what do we always do? We list the genotypes and we list the phenotypes. So let's work out what the possible genotypes are. This is going to be a really big, long list. Generally, it's nice if you break it up, and we sort of often start with all the possible backup combinations for one at a time. So for every individual that's homozygous dominant for, we'll say this is nose color, they could be homozygous for tooth size, they could be heterozygous for tooth size, they could be homozygous recessive for tooth size. So we would have those three possibles. Well, then we could have individuals who are heterozygous for nose color. And they could be homozygous dominant for tooth size, or heterozygous, or they could be homozygous recessive. Can you guess how many more we have? 3! Yeah, because we could also have individuals who are homozygous recessive. I'm going to make this easier on myself by copying that. And you can actually, if you're working in Docere, you can copy that too. Okay. So now we have to go through and tally. And if we look for big N, big D, I see 1. That's all I see. If we look for big N, big D, little d, I see 2. And big N, little d, I see 1. Does that ratio seem familiar to you, 1 to 2 to 1? Yeah. So for individuals who are homozygous dominant for nose color, they're 1 to 2 to 1 in terms of their inheritance for tooth size. Okay, now let's look at individuals that are heterozygous for nose color. So I see big N, big D, big N, little n, big D. I see 2. Then, let's see, I'm going to do this. Big N, big D, big N, little d. Well, I see 4. And Big N, I'll do this in purple. Little d, I see 2. Huh. Look at that pattern. Anybody have a prediction about what the pattern will be for the last 3 genotypes? 1, 2, 1. Well, I think you're right. Let's test that. So, little n, big D, 1. Little n, heterozygous, 2. Oh, gee, 1 left. Yeah. So we see this larger 1 to 2 to 1 to 2 to 4 to 2 to 1 to 2 to 1. It's crazy. But it's got this sort of pattern within a pattern. I like it for that reason. So if you had to make predictions without doing any counting or any figuring yet about the phenotype ratios, do you think there's any echo from the older pattern type? So the older pattern type is 3 to 1. So let's go ahead and take a look. Okay, so what are our possible genotypes here? Let's assume that we have, what is it, black nose, pink, was it black nose, pink nose in the beavers? Okay, I know we started off with humans, but hey, what the heck, maybe we have black and pink nosed humans. And for tooth size, big D, I think, was big teeth, long teeth, large teeth, large teeth. Okay, so what are our possible combinations? How many phenotypes do we have? Well, how many? You think there are 16 phenotypes? Well, let's see. So we could have an individual who comes out with a black nose and long teeth, right? We could have an individual who comes out with a black nose but short teeth. We could have an individual who comes out with a pink nose and long teeth. We could have an individual who comes out with a pink nose and short teeth. Are there any other possible phenotype combinations? It's just 4. There are 4 phenotype combinations. So there are more genotype combinations, but there are only 4. There are always, in Mendelian traits, there are always fewer phenotype combinations than genotype combinations because those heterozygous individuals are going to appear phenotypically like a dominant individual. So if we look at our numbers here, who has a black nose? Where are our black-nosed individuals? If we look at the genotype ratios, are any of these pink-nosed? No, those are all black-nosed. What about these heterozygous individuals, heterozygous for nose color? Are they pink-nosed or black-nosed? Black-nosed. So we know all of those guys are black-nosed. Okay, what about these? Large teeth, short teeth. Large teeth. And I find it easy to make tallies and then put in my numbers. Okay, what about these guys? Long teeth, short teeth. So 2 more. And down here, and this one's going to be a short tooth, so we'll put 1 there. This one's going to be what? Long teeth. And we're going to get 4 out of that. 1, 2, 3, 4. Dominant phenotype. So our total for that is 9. Okay, and then these black nose, short teeth. Total of 2. So we know that all of these are pink noses. How many have a pink nose and long teeth? 3. And I'm going to change this to pink to kind of correspond there. So these guys are all pink noses, and these 3 all have long teeth. So who is the one little offspring in the family who's got a pink nose and short teeth? Just this one. Just one left. Wait, something's not right here. Ah! Wait a second. Did I screw something up? I did! I sure did. Should be 9 to 3 to 3 to 1. What about this one? There's one there. So if we have 2 heterozygous individuals for any traits cross and we do a dihybrid Punnett square, we see a 1 to 2 to 1 to 2 to 4 to 2 to 1 to 2 to 1 genotype ratio, and we see a 9 to 3 to 3 to 1 phenotype ratio. If we express this as a percentage of the number that have a dominant phenotype on both characteristics, how would we do that? What percentage of the offspring would be expected to have a dominant phenotype for both characteristics? I'm going to tell you that this is very much an error test style question where you have to know to do the Punnett square, and they don't tell you list your genotype and phenotype ratios. They would just say what percentage of offspring would be expected to have a dominant phenotype for both characteristics. So how would we figure that out? Figure out percentage of anything. Percentage you got on your test. You got 14 out of 17. How do you figure out your percentage? 14 divided by 17. It's always the part divided by the whole. How many sort of hypothetical offspring are we showing here? 9 plus 3 plus 3 plus 1. 16. 16 offspring. Can't spell offspring. How would we figure out the percentage that would be expected to have dominant phenotype for both characteristics? What divided by 16? 9 divided by 16. So 9 divided by 16 times 100. 9 divided by 16. So a little over half of the offspring you would expect to be dominant for both characteristics. What percentage of their offspring would you expect to be recessive for both characteristics? Go ahead, you can use a calculator. Okay, so that's how you do a dihybrid Punnett square. I would say that it's your mission should you choose to accept it, but you don't really have it. Well, you have a choice. You could take a 0. But especially after our little talks yesterday about, what people need to do to get where they need to be for the end of the year, you don't want to do that. Your job on that packet, I believe do you have 1 or 2 more that have dihybrids? 2. So you're going to do 2 more dihybrids with heterozygous parents. Do you still have your beaver gamete packets with all the genes, all the traits? Do you want to put that up on the board? You can pick any 2 traits, but you have to have 2 heterozygous parents for every trait, because this is the most complicated one. And I want to start you off on the most complicated one, and you can work backwards actually more easily than you can build out. It sounds counterintuitive, but it's true. So I will pop up the traits for the beavers. Is that them? No, that's not them. That's not them. So that gives you the traits. Go ahead and pick any traits you want. Remember, 2 heterozygous parents. Show your gamete possibilities. And when you're all done with this, you're going to have sex-linked for the monohybrids. You're going to have dihybrids back here. You're welcome to use sex as a determining factor here. or use sex as a trait that you're crossing here. We're not talking about a sex-linked trait. You're just talking about sex. So it would be, how many long-clawed females versus short-clawed males versus long-clawed. You get the picture. So you can use any traits you want. Do 2 dihybrid crosses. You can work with somebody, but you all have to show every bit of the work. And while you're doing that, I'm going to call up people who I didn't get to yesterday to talk about sort of your roadmap for the end of the year.